now we want to ask what happens as omega 1 approaches omega naught. That is, as our driving frequency approaches the natural frequency of the oscillator. Well, as omega 1 approaches omega naught, first thing that happens is beta gets much smaller, beta being the difference between omega 1 and omega naught. So that our sine beta t function, which forms the envelope within which the oscillations occur, develops a longer and longer period. As omega 1 approaches omega naught, the period of this sine function approaches infinity, for the simple reason that beta approaches 0. As beta approaches 0, it's going to take beta t a longer and longer time to change by 2 pi, and clearly the time required to do so is going to approach infinity. In the meantime, omega 1 stays close to omega naught, so omega bar is going to stay close to both omega 1 and omega naught. And it's just, if omega 1 is close to omega naught, then so is omega bar, which is just the average of omega 1 and omega naught. So omega bar isn't going to change very much at all. So our sine of omega bar t is going to retain the same period, but the sine of our beta t function, which is multiplied by this function, is going to approach infinity. So that the period of this oscillation in here is not going to change much, but the period of this envelope is going to extend on toward infinity. Now, at the same time, the amplitude of this envelope is going to change. The amplitude of the envelope is your 2f over m divided by omega naught squared minus omega 1 squared. It's very clear that as omega 1 approaches omega naught, this denominator is going to approach 0, which is going to cause the value of this function to approach infinity. So we can represent the behavior fairly easily. If omega 1 is close to omega naught, then you have a small value of beta, which makes sine beta, gives sine beta a long period. So the period of sine beta extends. And omega bar stays pretty much close to omega naught as long as omega 1 is close to omega naught. And since omega 1 is approaching omega naught, that's certainly going to be the case. So what we end up with is lots of cycles of the sine of omega bar t in one cycle of the sine of beta t. So that our cycles of omega bar t are going to have a period like this, and many of these periods are going to fit inside of one half cycle of the sine of beta t. So that as omega 1 approaches omega naught, this time scale from here to here is going to increase. The time scale of these oscillations is going to remain constant, so that we could begin to depict the situation when omega 1 is closer to omega naught. We're going to have a longer period. Time scale is going to be greater, so that the time scale from here to here is going to be longer than it is from here to here. The period of the sine of omega bar t is not going to change appreciably, so that there are going to be more of these inside of a half cycle of the sine of beta t. Now, another thing that happens, and I'm not going to work through the details of that, that should be left for a problem for you to work out, is that the slope of the initial slope of this sine function, if I draw a tangent line here and draw another tangent line down here to the envelope formed by the sine of beta t function, this slope is going to remain pretty much the same. This is because as this time scale expands, so does the amplitude of this sine function that's forming the envelope, the sine of beta t. So this amplitude gets bigger as this gets bigger, and you can see whether those both change linearly. Again, that's a question I'll leave to you. But I will say that in the limit, at least, there is a limiting slope here. And we're approaching that limit as omega 1 approaches omega naught. So that there's an interval of this sine of beta t function, and maybe we indicate that interval by putting a little circle around it and bringing it down here. There's an interval in which the envelope of the sine beta t function, or the value of the sine beta t function, doesn't differ much from this initial tangent line. And within that domain, you have what I'll call a near linear domain. A segment of this hump here, which doesn't vary much from the linear function. And in that near linear domain, you have a nearly linear increase in the amplitude of the actual oscillation, which occurs at frequency, angular frequency, omega bar. Now, the limiting behavior as omega 1 approaches omega bar is that the period of the sine of beta t function approaches infinity. The period of this thing goes on to infinity, so that this hump here would depict a longer and longer time scale with more and more oscillations within the linear domain. And of course, the linear domain, as tightly as you want to define the linear domain, as close as you want to keep the sine beta t function to the tangent line, that linear domain, however you want to define it, also approaches infinite length, because as this approaches an infinite length, so does this. So that the limiting behavior is that the amplitude, well, let's not yet talk about the amplitude. That's just involved in the fact that we do approach a constant or a specific slope here. But the linear domain approaches the interval 0, infinity, just as the domain of this one hump of the sine beta t function does. Now, the amplitude of this hump does approach infinity, as we said, which is what allows the slope to remain constant. As the length of this interval approaches infinity, so does the amplitude of this half cycle of the sine function. And they both approach infinity in such a way that the limit here is constant, and possibly the slope is in fact constant throughout the approach to infinity. Okay, when this happens, we have an amplitude that starts small, gets bigger and bigger and bigger and bigger, and never stops getting bigger. Now, that behavior is theoretical, because in any actual physical system, there's always some sort of drag or inhibition in the system, and you don't actually get an unlimited increase in amplitude. But the theoretical behavior, if you ignore those inhibiting factors, is an ever-increasing amplitude, an ever-increasing energy, and this phenomenon we call resonance. There's a lot more I could say at this point, but these are ideas for you to engage with and work out on your own, so that you develop a deeper intuition about this thing. But it comes out of some fairly straightforward equations and some fairly straightforward behaviors of trigonometric functions. I'll mention that this is all one of the reasons why in the very early part of the course I confronted you with a lot of problems regarding the behavior of trigonometric functions and their graphs and so forth. A subject which is severely undertaught in high school analysis, college level pre-calculus courses. where the students who are bright enough to understand these behaviors are not challenged at a level beyond which a slightly below average student could achieve without working very hard. I'll step off of my soapbox and we'll move on to the next clip.